Breadth first search. Consider the following algorithmic problems in graphs. Is a given graph connected? Is a given graph bipartite? Given a graph and two of its vertices, determine a shortest path joining these two vertices. Problems like these and many others can be solved by simply traversing the graph. Graph traversal, also known as graph search, means visiting every vertex exactly once in a well-defined order. There are many ways to traverse a graph. Each traversal strategy is characterized by the order in which the vertices are visited. Breadth first search and depth first search are the most commonly used approaches. In this video, you will learn about the breadth first search algorithm. Breadth first search, BFS. BFS is a graph traversal algorithm that starts from a selected node, called source or starting node, and traverses the graph layer by layer, according to the distance to the starting node. As the name suggests, the algorithm traverses the graph breadthwise in the following way. First, choose any vertex as the starting node and visit it. Second, visit all nodes at distance 1 from the starting node. In other words, visit the neighbors of the starting node. Third, visit all nodes at distance 2 from the starting node. And so on, until visit all nodes. The algorithm can be understood as moving out in waves from a given point. For example, let us apply the BFS to the graph below. Suppose we choose the node A as the starting node. We mark it as visited. The next step is, visit all nodes at distance 1 from A. They are nodes B and C. The next step is, visit all nodes at distance 2 from A. They are nodes D, E, F, and G. The next step is, visit all nodes at distance 3 from A. They are nodes H, I, J, and K. At this point, all nodes have been visited. And the algorithm is finished. As you can see, during a traversal, it is important that you track which vertices have been visited, because the graph can contain cycles, which may bring you to the same node again while traversing it. To avoid processing of same node again, use a Boolean array, which marks the node after it is processed. Also, while traversing the graph, one can mark the edges that reach a new unvisited vertex. These edges are colored in red. The graph induced by these edges is a spanning tree of the given graph, and it is called BFS tree. This tree contains a shortest path joining the starting node to any other node. For example, a shortest path from the starting node A to node J is formed by the sequence A, C, F, and J. The data structure that precisely describes the step-by-step walkthrough of the breadth first search is a queue. A more precise description of the BFS algorithm is the following. First, initialize a queue with any starting vertex, and mark it as visited. All the other vertices are initialized as unvisited. Second, while the queue is not empty, take the next vertex V from the queue, and remove it from the queue. For each unvisited vertex W adjacent to V, mark W as visited, and insert it in the queue. To illustrate the algorithm, let us apply it to the previous example. Let us initialize a queue with the starting vertex A, and mark it as visited. Then, the queue is not empty. So, we take the next vertex from the queue, which is the vertex A, and remove it from the queue. For each unvisited vertex adjacent to A, we mark it as visited, and insert it into the queue. So, we mark B and C as visited, and insert them into the queue. Again, we take the next vertex from the queue, vertex B, and remove it from the queue. For each unvisited vertex adjacent to B, we mark it as visited, and insert it into the queue. So, we mark the vertex E as visited, and insert it into the queue. We take the next vertex from the queue, vertex C, and remove it from the queue. For each unvisited vertex adjacent to C, we mark it as visited, and insert it into the queue. So, we mark the vertices D, F, and G as visited, and insert them into the queue. The order in which the vertices are marked and inserted into the queue depend upon the order they are reached in the data structure that is used to represent the graph. Following the algorithm, take the next vertex from the queue, vertex E, and remove it from the queue. For each unvisited vertex adjacent to E, mark it as visited, and insert it into the queue. So, we mark the vertex H as visited, and insert it into the queue. Following the algorithm, take the next vertex from the queue, vertex D, and remove it from the queue. For each unvisited vertex adjacent to D, mark it as visited, and insert it into the queue. Every vertex adjacent to D is visited. So, nothing is done. Following the algorithm, take the next vertex from the queue, vertex F, and remove it from the queue. For each unvisited vertex adjacent to F, mark it as visited, and insert it into the queue. So, we mark the vertices K and J as visited, and insert them into the queue. Following the algorithm, take the next vertex from the queue, vertex G, and remove it from the queue. For each unvisited vertex adjacent to G, mark it as visited, and insert it into the queue. So, we mark the vertex I as visited, and insert it into the queue. Following the algorithm, take the next vertex from the queue, vertex H, and remove it from the queue. For each unvisited vertex adjacent to H, mark it as visited, and insert it into the queue. As every vertex adjacent to H is visited, nothing is done. The same occurs with the remaining vertices in the queue. They are simply removed, one by one, until the queue is empty. The algorithm is finished.